This is the story of a quest for evidence, prized from an unforgiving soil, dug from caves deep underground. Clues pieced together to reveal giant creatures from the Earth's far distant past, how they lived, and why they died. Like detectives on a murder hunt, scientists are using forensic techniques to unlock the secret of what killed the megabeasts. And their quest for clues will take them on a trip back through time. The age of the megabeasts reached its peak at the beginning of the Pleistocene, nearly 2 million years ago. During the Pleistocene epoch, the megabeasts dominated the four corners of the Earth, from North America to New Zealand. Most were mammals, some were marsupials, all were big. But like the dinosaurs millions of years before, all this suddenly changed. The megabeasts began to die out. The scale of the extinction was mind-boggling. In a blip of cosmic time, entire populations simply vanished. First to go were Australia's megabeasts, around 50,000 years ago. Victims included a ferocious predator, the marsupial lion.
The marsupial lion was a bruiser, built to give hard hits and built to take hard hits.
The axe next fell on the Americas. Around 11,000 years ago, the extinctions here claimed a bizarre range of species. The incredible giant ground sloth, the more familiar woolly mammoth, and the monstrous giant beaver, to name but a few.
The thing that's important is that these were the big guys. We had large mammals in great diversity and in high numbers. They ruled.
Still, the demise of the megabeasts continued. Off the African coast some 2,000 years ago, extinction next claimed the massive animals of Madagascar, animals like the giant lemur.
Can you imagine a primate with eyes on the side of the head like a cow, a long snout? They're not like any creature anywhere on Earth.
And the destruction finally ended on the remote islands of New Zealand. The date, just 700 years ago. The victim here, a 9-foot-high, flightless bird called the moa. The world's megabeasts were united by just one thing, their size. But what singled them out for destruction remains a mystery. Unlike the dinosaurs, victims of a meteor impact, no single event explains the megabeast decline. The cause of their demise has become the subject of fierce debate. Some believe that extinction must have come at the hands of human hunters. They call it the kill theory.
Oh, I think the part humans played is total. I think it is the crucial difference. There would not have been this wave of large animal loss without human involvement.
Others believe in chill, that dramatic temperature change at the end of the last ice age holds the key.
The climate was undergoing rapid, profound changes. Unquestionably, the most dramatic climatic changes that we've seen on the planet in the past 20,000 years.
And still others advance a new idea. The ill theory. The killer, they say, was disease.
You could have a series of killer plagues, not only in the species in the immediate vicinity, but spreading like a rolling wave, species after species, becoming infected by these killer microbes.
But no one agrees. So far, no one has come up with one theory to fit all places and all circumstances. The hunt was on to unravel one of the biggest mysteries of the prehistoric era, the greatest animal extinction since the dinosaurs. The search would hinge on the competing theories of kill, chill, and ill. But the Pleistocene world would not give up its secrets easily. This is the first place where scientists might expect to get answers: Australia. It's here that the Pleistocene world is at its oldest. It's here that the trail of megabeast extinctions first began some 50,000 years ago. Yet it's here that the mystery is deepest. In common with many other parts of the Pleistocene world, Australia was a prehistoric wonderland.
If you could have visited Australia 50,000 years ago, there would have been big animals everywhere, but they would have been completely foreign and alien. You would have seen giant turtles the size of VWs with horns like cattle, giant wombats perhaps the size of a rhinoceros, and huge duck-like birds twice the size of an emu. It would have been a bizarre fauna, and I would have given anything to see it.
Crucially, the Australian bush was also home to megabeasts that bit back. And one animal, above all others, stood out as the most fearsome. On a long-lost day 50,000 years ago, two hunters stalked a herd of grazing animals. Little did they know that they too were about to become the hunted. They had strayed into the path of a ferocious megabeast predator that dominated prehistoric Australia, the marsupial lion, Thylacoleo carnifex.
Thylacoleo is probably best looked at as a giant homicidal wombat. These massive slicing cheek teeth were like bolt cutters. A pair of these could literally have ripped the arm off any human being. It would not have been a particularly graceful animal. This is an animal that was built for power.
The marsupial lion was a prehistoric bushwhacker with just one aim: but even a killer like this could sometimes fall prey to forces beyond its control. Beneath the bush, a 40-foot drop to oblivion. The marsupial lion had fallen foul of a treacherous feature of Australia's ancient landscape, a giant sinkhole caused by the partial collapse of a cave roof. It was now trapped underground with no way out.
An animal like the marsupial lion would have perhaps stumbled, tripped, fallen into that cave. It may have died on impact, or it may have suffered a more lingering death through dehydration and or hunger.
An accident claimed the life of this marsupial lion. Such accidents do not explain extinction, but they can help preserve clues to its cause. This is Wellington Cave, 300 miles north of Sydney. It was here that scientists first found the remains of a marsupial lion, along with hundreds of other prehistoric animals, all trapped by sinkholes, all preserved underground. The bones were prime pieces of evidence, but would they help reveal what killed Australia's megabeasts? Like forensic detectives, scientists needed first to date the age of the bones. Time of death could establish cause of death. If the extinction followed a time of climate change, then the chill theory might hold true. If the megabeasts died out in the wake of human arrival in Australia, then the cause could be kill. If those humans brought disease, then maybe it was ill. But in Australia, dating of fossil bones is anything but easy. Scientists have found that bones are too old, too fragmented, too few in number to offer consistent findings. So they've tried instead to date the soil and sand in which the bones were found. Soil age, they reasoned, could provide evidence of bone age. And indeed, the technique has revealed an extinction date close to the date of human arrival in Australia. That points to kill, but the proof is hardly conclusive.
It's very hard to interpret the data we have at the moment in terms of the cause of the extinction. If we look at individual bones, it may have been they were first buried 1 million years ago and were then dug up through a creek or water or something, erosion, and the bone moved into another locality and reburied again.
Science can only hint at the cause of the Australian megabeast extinction. For the marsupial lion, the file must remain open, pending further investigation. To solve the mystery of what killed the megabeasts, whether killed, chill, or ill, scientists would need younger bones, fresher clues. And the hunt for those clues was to begin half a world away, in America. These men have set out to prove the chill theory. Russ Graham and Ken Tankersley are Pleistocene scientists with an interest in ancient weather systems. Their quest has taken them underground to a site never before filmed, Sheridan Cave, Ohio. Sheridan is a Pleistocene gold mine. Excavations here have revealed the bones of now extinct species like the giant stag moose and the short-faced bear. But Graham and Tankersley are interested in one very special animal, a creature that for them symbolizes the fate of all the megabeasts in North America and perhaps worldwide. Castroides ohioensis, the giant beaver. Next to the skull of a modern beaver, the giant beaver looks massive. The biggest known specimens could measure 9 feet from nose to tail and weigh as much as 1,000 pounds. At its peak, the giant beaver had dominated the wetlands of prehistoric North America like some kind of aquatic grizzly bear. But then, it began to die out. Tankersley and Graham have come to Sheridan Cave because it was here the remains of the most recently discovered giant beaver were found. And the story behind its demise, they say, is also the story of how chill worked to kill all the megabeasts around the world. "23,000 years ago, midway between the Australian and American waves of megabeast extinctions, freezing weather held the Earth in an icy grip. The global winter lasted for 6,000 years. Conditions were extreme. Scientists call it the Ice Age. A massive glacier had spread across the Earth. Large areas of Europe and North America were buried under tons of ice. But then, 16,000 years ago, the ice began to melt. The Earth got suddenly warmer. In the wake of Earth's temperature rise, rich grasslands rapidly sprang into life, and animals, previously driven south by the ice, began to return. But the forces that created this brand new Eden were also destined to destroy it. Melting glaciers released huge walls of water. The deluge flooded the land for thousands of square miles, flattening everything in its path. But the massive flooding, according to chill theorists like Russ Graham, is only half the story. What killed the giant beaver and dozens of other megabeasts was the sudden temperature change that came with it.
The Ice Age, Pleistocene, was a very dynamic time globally. The climate changed very abruptly, probably within the lifetime of a human being. Within 40 years, we went from the Ice Age to the Holocene, a warm time period. And it's that abrupt change that I think caused the extinction.
The giant beaver remains found at Sheridan Cave show how uniquely adapted to its environment the animal was.
The giant beaver had very, very different front teeth, not only because of their enormous size, but the angle of the teeth as well, which were specifically adapted for exploiting or acquiring marshy, rushy vegetation that we find typically in wetlands which dotted the landscape near the end of the last ice age.
This physical adaptation to a specific landscape was to prove the beaver's doom. As the massive glacial flood swamped its natural habitat, the plant life vital to the giant beaver's survival slowly disappeared. That was bad enough, but it got worse. For 11,000 years ago, the temperature began once more to fall. Meteorologists today call it a cold snap. It was to last 1,000 years. Another period of chill meant the land became dry and arid. The giant beaver now had nothing to eat and nothing to drink. Unable to adapt to a world of rapid climatic upheaval, the giant beaver faced certain death. Yet astonishingly, the giant beaver's smaller cousin, itself a veteran of the Pleistocene, continued to live on to the modern era.
The question is, after climate change, why did only the modern beaver survive? I would argue that the modern beaver creates its own habitat, creates its own ecosystem. It builds dams, it builds lodges, whereas the giant beaver was dependent upon a very specific environment that only existed during the Pleistocene.
All over North America, this pattern was repeated for many other species. The small animals adapted to the suddenly changed conditions, but the big animals needed too much food, too much shelter, too much real estate. As they searched for the habitats they had lost, the megabeasts broke up into smaller and smaller groups, widely separated. For thousands of years, the giant beaver population ranged across the eastern United States. 2,000 years after the end of the Ice Age, its numbers dwindled to the point where only one animal was left. In Sheridan Cave, Ohio. It was here that the giant beaver made its last stand.
Sheridan Cave provided a refuge where water was present. The giant beaver would have climbed into the cave looking for water, but also looking for the habitat that it needed for survival, which provided the foodstuffs that it needed, these marshy rushes. They weren't here, and the beaver did die.
Dating of the giant beaver's remains confirmed it was the last known example of its kind anywhere. Soil analysis has also revealed the giant beaver died while the climate was cold and dry. For Russ Graham, the dating is significant.
We know that at the same time the megafauna went extinct, the climate changed very abruptly. We also know that the habitats the animals were adapted to disappeared at this time, and we also know from being able to map the distributions of these animals that their geographic distribution was at a minimum size at the time of the extinction. We feel very strongly that it's all of these factors that add up to build the case for climate change as the cause of the terminal Pleistocene extinction.
The giant beaver bones found in Sheridan Cave make for a compelling case, but doubts still surround the chill theory. Critics point out that ice ages were not new. For the last 100,000 years of the Pleistocene epoch, the Earth had suffered as many as 23 distinct ice ages. The megabeasts had lived through 22 of them. The 23rd was no different. some other factor must have been at work. For 2 decades, this man has puzzled over the mystery factor.
I went to the field 20 years ago fully expecting to find firm evidence that it was climate that was killing these large animals at the end of the Pleistocene. But the more I thought about this problem of extinction, it occurred to me that something else had to be added to the equation.
It was the end of the Ice Age. As human nomads migrated to lands made newly habitable by the warming sun, they encountered a new range of animals. Animals that had not yet learned fear of man. The humans were expert hunters. Fanning out, they quickly encircled the leader of a small herd of mammoths. Take down the leader, and the herd becomes easy prey. This is a spot where scientists agree a mammoth slaughter actually occurred. It doesn't look like much now. A small ridge cut by railway lines snaking through remote farmland in Colorado, some 40 miles north of Denver. The spot has a name: Dent. Over 60 years ago, paleontologists working at Dent made the mega beast find of the century. Jumbled together the bones of no less than 15 woolly mammoths. Littered among them, man-made spear and arrowheads. Evidence of a mammoth massacre. For kill theorists like Gary Haynes, what happened here was proof that overhunting wiped out the megabeasts in one fell swoop.
This is the place right here that should be honored as the first real identifying place in North America that gave us the germ of an idea that maybe the megafauna, the mammoths and the mastodons and other large animals in North America had been hunted by people and possibly hunted to extermination.
Dent wasn't the only kill site that scientists have found in North America. Since the 1930s, some 14 other sites have been uncovered, containing the speared and butchered bones of over 80 megabeasts, mainly mammoths and their cousin, the mastodon. For some, this was proof positive of a pattern of hunting and killing on a massive scale. The kill theory was born. In fact, the case for kill seemed open and shut. Humans had both opportunity and motive for megabeast extermination.
The kinds of animals that disappear, they are the kinds of large animals that I think of as preferred prey. The kind of creatures that would attract hunters or foragers in new lands, the biggest. And the disappearance is critical. It's in step with the arrival of our species in different parts of the world.
Worldwide human migration mirrors almost exactly the pattern of megabeast extinction. 50,000 years ago, Australia. 11,000 years ago, the Americas. 2,000 years ago, Madagascar. 700 years ago, New Zealand. Everywhere the story is the same. Where humans turn up, the big animals die. Whatever the theory, hunting is a practical business. Gary Haynes is an expert in the kind of weapons primitive humans might have used to bring down the megabeasts. Mammoths were big. Killing these leviathans would have required powerful weapons. Weapons that, according to Haynes, Stone Age man possessed.
They're arrows or spears. This one here is a long single wooden spear with a fluted point attached at the end firmly. This one was probably used to either throw or thrust into the bodies of the animals, so the hunters had to be very close to them to use this. There have been some studies done with these that indicate that a spear thrown overhand using a spear thrower can penetrate quite deeply even into something solid like plywood, and it certainly would have done some major damage.
Stone Age humans may have had sufficient means for megabeast extermination. But why kill so many giant animals when one alone could easily feed an entire community? For kill theorists, at least, nature provides an answer. In the wild, some predators have proved capable of surplus killing.
Hyenas have been observed, for example, to prey upon gazelle, their favorite prey, in a very destructive way. They would kill them in much larger numbers than the hyenas could consume. This is called surplus killing. It is known among a variety of different predators.
The megabeasts had never seen humans before and didn't recognize them as predators. They were easy to kill. And for Martin, at least, humans will kill such animals just because they can. Kill makes a compelling case for the demise of one type of megabeast in North America. But could it explain the end of megabeasts worldwide? Kill theorists needed to find more kill sites, more species, more proof on a grander scale. In a forgotten corner of a museum in York, England, stand the remains of a creature whose fate provides the strongest evidence yet for the kill theory that what killed the megabeasts was man. The animal is, by any standards, a bizarre one. A 9-foot-high, 500-pound flightless bird called the moa. The moa had once dominated the landscape of an island in the far South Pacific, New Zealand. For millions of years in New Zealand's rainforests, the moa had flourished. It was one of the largest birds to ever walk the earth, but it couldn't fly.
Moas are the only birds in the world which did not have wing bones at all. Some of them did not even have the sockets for wing bones to go in, so they were the ultimate walking birds. They were herbivores. They ate a variety of vegetation. Some consumed some of the roughest forage you could possibly think of.
Today, scientists are still on the hunt for moa remains. Here in the Bell Hill Vineyard north of Christchurch, they've made an exciting find, exclusively revealed for this film. A massive moa bone site. It's the first such discovery in over 50 years. On the side of a hill, a small stream cuts a gully. The soil, when mixed with water, creates a thick and sticky mud, perfect for preserving the remains of an ancient forest. And of course, clues, like bones. Bones that show evidence of massacre. Richard Holdaway is a moa detective. Before establishing how the moa died, he must first piece together how it lived.
They were very large and robust animals, but they did not have almost certainly any defence mechanism against predators other than birds of prey. So the birds would have been living in pairs or small groups, dispersed through the forest, taking advantage of whatever vegetation was in there.
Slow moving, slow eating, the moa knew nothing of the dangers posed by predators. The most any moa was likely to face was a squabble with a neighbor for food. The moa was a living fossil, a throwback to the prehistoric world that somehow had escaped extinction. Perhaps the bird was lucky. Perhaps it hadn't yet encountered man. All that changed 700 years ago. That was when Polynesian mariners first discovered New Zealand. Their impact on the moa was swift and brutal.
New Zealand was the last temperate landmass to be settled by people, so all the wildlife here was naive. It had seen no mammalian predators in its entire evolutionary history. So when the first humans walked up the beach when there was a moa standing there, it wouldn't have recognised them as being a threat, and they could have hit it on the head quite easily. And the extinction took place so rapidly, in terms of a few decades over the whole country, maybe a century at the most, that none of them would have had a chance to learn fear of humans.
What happened next, claim kill theorists, is a template for what happened to the megabeasts worldwide. Using primitive methods, the Polynesians began taking out the moa, one by one. Back at the Vineyard Bone site, a sudden burst of bad weather brought the dig to a halt. Richard Holdaway took the opportunity to reflect on what the discoveries here and at other sites have revealed about the moa and the people who hunted them.
The Polynesians, as anyone anywhere in the world, when they're in a hostile environment where there are limited food resources, took advantage of every source there is. They took the adults, they took the young, and they took the eggs.
The bones recovered at Bell Hill Vineyard and elsewhere reveal a graphic record of what happened. The evidence is still surprisingly fresh. Bones charred by cooking fires. Bones cut by spears. Bones gnawed by teeth. The moa rapidly became central to the Polynesian settlers' way of life. The Polynesians made necklaces and fish hooks from moa leg bones. They used moa feathers for clothing. They used moa eggs as water containers. Moa was on the menu day and night. Some nights the fires would stretch to the horizon. In less than a century, 170,000 birds are thought to have perished. The moa's demise was rapid, and to this day their fate remains the most convincing example of extinction by overkill.
The New Zealand situation, the New Zealand extinction event, is the best available to look at human impact directly, because it is so recent. the gun's still smoking. We can actually see the cooked animals in the ground. We can see on a site like Bell Hill Vineyard, you can see what it was like immediately before that. We can see the mowers, we can see the age structure of the population, we can see the trees, we can see the seeds in the trees, we've even got the snails in the soil. It has to be teased apart, and it's tricky under the conditions sometimes, but the record is so complete that there is no better example in the world. It's horrendous, but it's true. We live in a laboratory of cataclysm.
The Moa's end was dramatic, but many scientists remain unconvinced that the giant bird's fate points to the fate of the megabeasts as a whole. The Moa's demise, they say, was a rare event. The bird was trapped on an island with a finite population and nowhere to run when the hunters came for them. The kill theory, like the climate-based chill theory before it, works for some scenarios, but not for all. Whatever killed the megabeasts must have been fast, ferocious, and insatiable, something that reached out across the world and struck down dozens of giant animal species in a short space of time. But what on earth could it have been? In 1918, just after the end of World War I, people across Europe suddenly began falling sick. At first, it seemed they'd caught a kind of feverish cold. But it turned out to be something much worse. Something that might point the way to solving the riddle of what killed the megabeasts. In time, the killer was identified. It was a virus, and it may have jumped to man from another species. Its name, influenza. Ross McPhee is curator of mammals at the American Museum of Natural History in New York. McPhee has long been skeptical of the standard explanations for the megabeast extinction. He's come to believe that the giant creatures succumbed to an epidemic that jumped between species. Not the flu that struck the world in 1918. But a microscopic monster every bit as bad.
One of the really puzzling things about extinctions is simple. Do they happen really quickly or do they happen slowly? A lot of my colleagues think that extinction can take hundreds or even thousands of years to come into effect. I think differently. I think most extinctions that have happened in the course of Earth history have happened like that, virtually overnight. So what we need to cause an extinction, particularly a lot of extinctions at once, is something really unusual, really remarkable that the animals have not had to deal with beforehand. There's not much in life that could do that, but how about a virus?
Viruses are one of nature's great mysteries. Hit-and-run killers that come seemingly out of nowhere and disappear equally fast. But to cause extinctions, a virus would have had to infect widely, kill quickly, and jump between species. McPhee gave his megabeast killer a name: hyperdisease.
We have to imagine extreme mortality. We have to imagine every individual or nearly every individual getting sick and possibly dying within a short period of time, like a few weeks.
McPhee's disease idea was dubbed the ill theory. It rapidly attracted criticism. In all of Earth's history, there had never been a proven example of a global epidemic jumping across so many species of animals at one time. But at a local level, animal populations can be decimated by species-jumping disease. British veterinarian Sarah Cleveland has seen firsthand the damage a species-jumping virus can do. Cleveland works in East Africa. For over 10 years, she's battled against a species-jumping disease that has run rampant through the local animal population. It's called canine distemper. It's a virus, and the way it operates today may offer a template for how hyperdisease worked in the prehistoric past.
You get a scenario whereby the virus spreads from domestic dogs to, let's say, a jackal, and then from a jackal to perhaps a hyena, and then perhaps from a hyena to a wild dog.
Canine distemper is rife among domestic dogs living on the edge of the Serengeti National Park. Contact between infected domestic dogs and African wild dogs, which have no natural immunity, sparked a deadly species-jumping plague. What canine distemper does to wild animals is not pretty. Swollen throat, foaming at the mouth, fits, and death.
You may start to get discharges from the nose, discharges from the eyes, and as it progresses and the virus then enters into the central nervous system, you get very dramatic effects with incoordination, paralysis, and at the most extreme end, these very dramatic, sort of epileptic type of seizures.
The plight of the wild dogs was made worse by their sociable nature. In the mathematics of extinction, animals that live in groups are more at risk than loners. It is perhaps an age-old rule. The African wild dog was virtually wiped out by canine distemper in just a few years. Worse still, the disease began attacking another group-living species, lions.
We estimate about 1,000 lions died in the whole of the Serengeti, which is approximately about 30% of the total population.
Maybe the fate of the lions and wild dogs of the Serengeti echoes the fate of dozens of giant prehistoric species too. Species like the Australian marsupial lion, the North American giant beaver, the woolly mammoth. Could all of them have succumbed to a global killer plague? Sarah Cleveland, for one, thinks they could. The reason, when on the brink of extinction, big animals don't bounce back as well as their smaller cousins.
In the late Pleistocene, there were probably a lot of large mammals that had very low reproductive rates. They lived a very long time. And disease probably had more severe consequences for that type of population than for a species that has very large litter sizes, reproduces very quickly, and can rebound much more quickly after an epidemic.
In the modern age, at least, disease doesn't always win. Cleveland has reduced the impact of canine distemper through vaccination. And for the African wild dog, it seems to be working. But 11,000 years ago, during the Pleistocene, there was no vaccine and no one to do the vaccinating. McPhee's disease theory sounded plausible, but he lacked one thing: evidence. To prove his idea, he'd have to find where the mystery virus had come from and how it operated. He needed to find a trigger. Exponents of the kill theory had noticed at the end of the last ice age a global link between megabeast extinctions and the first arrival of humans. They'd argued that humans had wiped out the megabeasts through hunting. But McPhee drew different conclusions.
The people come, perhaps they've walked a long distance over a land bridge, and they came in with a cloud of microbes around them, within them, on them, entered a place that they'd never been before. But once they started interacting with the animals, that same cloud of microbes was available to spread everywhere that it could.
Mammoths, along with other megabeasts, had no natural immunity to these newly introduced microbes. Domesticated dogs could have passed on the disease from their human masters, innocently carrying the seeds of the mammoth's doom. Hyperdisease. McPhee had found in human migration a possible trigger for hyperdisease. Now he needed to find physical evidence of a megabeast plague. McPhee knew he had one slim chance. The only trace microbes leave behind is genetic. Perhaps a new science could help solve an old mystery. When a virus attacks a cell, it generates proteins. These remain in the body's DNA. After death, the body decays, but DNA can stay preserved in soft tissue, like skin or hair. Amazingly, prehistoric soft tissue can still be found. The hunt for that tissue was to take McPhee on a trip to one of the most remote spots on Earth. And face to face with a creature that looked literally out of this world. This is Bahia Blanca. It's a tranquil spot some 400 miles south of Buenos Aires, Argentina. It seems hard to believe a beach like this could help solve the riddle of what killed the megabeasts. The debate turns on three competing theories: kill, chill, and ill. And Bahia Blanca was about to provide clues for one of them. Some 2 feet below the surface, perfectly preserved in the sand's soft sediment, local scientists have found fossilized footprints. It's an amazing discovery. The footprints are only accessible at low tide for just 4 weeks a year. The time available for their study is short. Yet there are hundreds of them, and they go on for miles. The footprints are big. Some are the size of bathtubs. But the creatures that made them were bigger still. In fact, they were monsters. For 11,000 years ago, Bahia Blanca was home to the giant ground sloth, Megatherium.
Megatherium was one of several species of ground sloths that existed in North and South America until about 11,000 years ago, Megatherium being one of the very largest. It's estimated that its body weight could have been as much as 5 or 6 tons, and even though they were armed with enormous, vicious-looking claws, they probably used those only to dig out roots and tubers, to defend themselves, and to dig burrows, perhaps.
Ross McPhee has come to Bahia Blanca to find out more about the giant sloth and its habits. He aims to prove the ill theory, and he's on the hunt for evidence of hyperdisease. And maybe the beasts of Monster Beach can give it to him. McPhee joined local paleontologist Sylvia Aramayo for a guided tour.
So you have a footprint here, a footprint here, and a footprint in the middle?
Yes.
Aramayo's measurements painted a vivid picture of the sloth in motion.
They were enormous animals, weighed about 4,000, 5,000 kilograms.
Yes,
enormously. You see, it's a very soft sediment, so it pushed easily.
Unlike skeletal remains, the tracks brought not only the animal to life, but its entire world. McPhee was impressed.
So what we have here is, what makes this so unusual, is that this is really fossilized behavior. It's not just bones and teeth. This is actually telling us something about how the animal moved.
11,000 years ago, the landscape here was very different. No beach, no sea. The sloth was foraging for food, using its height to spot the most luscious greenery. All this fascinated McPhee, but then Aramayo revealed something else. The giant sloth had not been the only animal to leave its tracks behind. Bahia Blanca, it turns out, was a megabeast highway. The beach is crisscrossed by the tracks of dozens of different prehistoric species, all moving and mixing together at once. For McPhee, that meant only one thing. Where animals get sociable, they get sick. The giant ground sloth of Bahia Blanca must have been vulnerable to disease.
What we know is that there were a lot of animals here, and they were from many different species, and they were congregating in very large numbers. In circumstances like that, it's easy to see how diseases could get started and get transmitted across species lines, which is basic to the hyperdisease idea.
Sharing the same water holes, McPhee reasoned, the megabeasts would have been exposed to a common spreader of disease: their dung. Dung would contain soft tissue, rich in DNA. In its turn, DNA could yield hard evidence of a species-killing plague. Inspired by what he'd seen on the beach of Bahia Blanca, McPhee began making plans for a dung hunt. It was perhaps the strangest quest of his career, and it would take him 1,000 miles south to one of the most remote spots on the planet, the southern tip of South America, Patagonia. Patagonia seems a land untouched by time. As the clouds swathe its jagged peaks, so Patagonia lies cloaked in the mystery of its past. If clues exist at all to support McPhee's ill theory, he'll find them here. Because Patagonia has a climate perfect for preservation. During most of the year, the temperature remains cold. So cold, even the lakes and rivers cannot support life. The air is dry. Rainfall is rare. It's a landscape that still bears the scars left by the end of the Ice Age. And glaciers still carve the windswept terrain. This was McPhee's destination, an enormous cave gouged out of the side of a wind-blown ridge. The locals call it Mylodon. Inside the cave, a moonscape of jumbled rocks and craters. Within each crater, a microenvironment, each defining a different aspect of the prehistoric world. Indeed, Mylodon had been home to megabeasts of all shapes and sizes, including the giant ground sloth. This is not the first time that scientists have visited Mylodon Cave. Indeed, the cave has had a long and distinguished history.
This cave was discovered near the end of the 19th century, and the first item which was found at this cave was a piece of hide, which turned out to be the remains, fossilized remains of a Mylodon, an extinct sloth. So the preservation of bones, soft tissue, and even plants here is just so good that it really attracted the attention of scientists all over the world.
McPhee joined a local excavation team and got straight to work in the dry, refrigerated soil. He was seeking giant sloth dung sufficiently well preserved for laboratory analysis. Sloth dung might contain DNA. Within sloth DNA, there might remain the telltale signs of a hyperdisease bacteria or virus.
Here at Mylodon Cave, there is a chance of going after soft tissues that might hold remains of viruses that I would not be able to access in any other way. So for that reason, it's fantastic to be able to sample here.
These are the kind of microscopic killers that McPhee has in his sights: bubonic plague, rabies, anthrax, a rogues gallery of diseases known to jump species and to kill. Traces of any one of them in Mylodon Cave would turn our understanding of the prehistoric world upside down. But the chances of finding dung containing intact genetic evidence of hyperdisease were vanishingly small. McPhee was engaged in a great scientific gamble. Layer by layer, the excavation team was stripping away millennia, but the task before them was a difficult one.
We are screening a total volume of about, let's say, 6 cubic meters. It's quite a big job, and it takes a long time to do it because we have to do it very carefully.
Time and again, the team found small bone fragments, fossilized plant remains, but the precious desiccated dung eluded them still. Then, quite suddenly, McPhee found what he'd come for.
This is it. We got one. This is a piece of dung. It's maybe 4 or 5 inches long. It's incomplete. This area here is clearly disturbed. That means that pieces of dung, which are quite light because they're all desiccated and dried out, get kicked around. But this is what I'm after. This demonstrates exactly what I'm after. So let's just see what we've got here. Okay, it's got a good consistency. Yep, it's going to come out as a piece.
This particular dung sample was already too contaminated for genetic analysis. So using his bare hands, McPhee decided to take a closer look at its physical makeup.
I'm looking at twigs, I'm looking at hair. There's a lot of hair in this. These animals are obviously grooming themselves or grooming each other.
The last time this hair had seen the light of day was on the back of a living giant sloth. McPhee was holding history in his hands, a history that was still surprisingly fresh.
You could go outside this cave right now and find droppings from cows that would look no better, no fresher than what I have in my hands here. So it's just absolutely fantastic. If degree of preservation is going to help us with this investigation, this is precisely what's needed.
McPhee enlisted the help of eminent New York geneticist Carol Reese. Reese has done work for the U.S. government seeking out deadly pathogens.
The kinds of diseases we're thinking about are things that are very nasty. Things like anthrax or rabies. Things like the plague, which could be spread from one animal to the next.
Reese and her team were looking for the remnants of the genetic packaging that long-dead pathogens leave behind.
When bacteria and viruses grow, they make copies of themselves. And these copies have many, many different proteins in them. And we're looking for the presence of the proteins left behind by the bacteria or viruses.
But in genetics, there are no shortcuts to success. The search is painstaking, a slow process of elimination.
Using an enzyme which recognizes the presence of the protein from the bacteria or the virus, we'll be able to see a color develop only where there was the specific protein present. And so if anthrax is not present in our sample, we're not going to get a color when we test for anthrax.
The color test revealed 11,000-year-old traces of the bacteria E. coli. But of anthrax and rabies, there was still no sign. In this kind of detective work, knowing what isn't there is as important as knowing what is. And Reese, for one, remains undaunted.
If we find it, it'll be fantastic. It'll be new. No one has ever done this before, and can give us tremendous insight into what happened and why these thousands of animals were just lost.
For now, at least, the gene hunt would have to go on. Like the competing theories of chill and kill, the ill theory has compelling arguments in its favor, but so far, no definitive proof. The mystery of what killed the megabeasts seems destined to remain a sleeping giant. Enter one final contender. David Burney is an ecologist at New York's Fordham University. He believes the hunt for what killed the megabeasts is in sore need of a rethink. And the best place to go and do that lies off the southeastern coast of Africa, in one of the last places the megabeasts lived and died. The hunt for what killed the megabeasts was about to take a startling and dramatic turn. Arab mariners call it the Island of the Moon. In its native tongue, it's the navel of the world. It lies just off the southeastern coast of Africa, a large island with a unique habitat, Madagascar. To American ecologist David Burney, Madagascar is nothing less than a Pleistocene laboratory. It's the place that could hold the key to what caused the greatest animal extinction in history.
Madagascar is among the most unique places in the world, both in terms of plants and animals, and perhaps most particularly in terms of the now extinct megafauna.
Burney has long puzzled over the mystery of the megabeast extinctions. As in other parts of the world, the demise of the giant animals in Madagascar seemed to coincide with the arrival on the island of humans. Humans first hit Madagascar some 2,000 years ago on outrigger canoes very much like these. Strangely, they came not from Africa, only 200 miles to the west, but from Indonesia, thousands of miles to the east. And what they found here must have astonished them.
Try to imagine a place where the largest grazing animals were cow-sized hippos. Tortoises here were larger than tortoises anywhere else in the world.
But in the wake of human arrival 2,000 years ago, the giant animals began to die. So complete was the destruction that on Madagascar today, no native mammal exists over 50 pounds in weight. But were humans to blame? Many scientists see in Madagascar signs of the kill theory. However, David Burney is not so sure. He's combed the island for evidence of overhunting by man, and he's found very little. So Burney has come back to Madagascar once again, this time to test a different theory. Maybe what killed the megabeasts was neither chill, kill, nor ill on its own, but a combination of all three. Burney is on the trail of an animal whose fate he believes has come to symbolize the demise of the megabeasts. He's searching not only for remains of the animal itself, but also for remains of the environment it lived in. It's a quest that has taken him and a team of scientists to the very tip of western Madagascar. Burney hopes the creature and its environment will cast some light upon causes of the mass extinction. As dawn breaks over the camp, Burney's team has some special visitors. Lemurs. The modern lemur is an agile tree dweller. Its body movements remarkably similar to humans. But it's the giant prehistoric ancestor of this sociable creature that Burney seeks. And that ancestor looked and behaved very differently. In fact, the giant lemur, Megaladapus, still provokes in David Burney a sense of awe.
Imagine a person who saw a Megaladapus alive and came back and told the people back home. They wouldn't believe it. This is the stuff of mythology. This is just such an incredible animal. Here is a A primate looks nothing like any living primate, with his eyes on the side of the head, big canine teeth, long snout.
Megaladapus was built to live in the trees. But for all its strength and agility as a tree dweller, the beast had a fatal flaw.
This was an animal maybe a little bit like the orangutan in one way, in that he was sort of the king of the trees, but you can almost imagine him being a bit of a clown on the ground because his fingers and toes were so long.
Remove it from its natural forest home, and the Megaladapus would have become quickly vulnerable to many threats. But which of those threats could have caused its extinction? To find out, Bernie means to walk in the creature's footsteps into a realm of ghosts. This is Bernie's destination, the caves of Anzuibe. It's a massive underground system carved painstakingly by the forces of nature. It covers many square miles, and its origins date back over 140,000 years. As with so much of the Pleistocene world, Bernie will find the clues he seeks underground. Deep within the island's massive cave system, he hopes to find animal remains that will yield clues as to what killed such a large array of extraordinary creatures. Bernie descends. The going is tough and sometimes risky. But the effort pays dividends. For here is a network of chambers that lead directly to the prehistoric past. Digging soon yields intriguing evidence.
A cave of this type here at Anzui Bay is a natural trap for animals. That's because there are many entrances of many different types. Large entrances with water dripping inside that would beckon to animals during the dry season to come in and have a drink and possibly get lost in the dark. And small entrances which an animal might use to hide in to try to escape from a predator, and then either be killed by the predator or dropping perhaps into a hole or a crack in the floor. And finally, the roof of this cave is like Swiss cheese, and there are dozens of places where an animal walking along in high grass could easily step and then drop 200 feet or more to its death.
Besides bones, Bernie's team is also taking soil samples.
What happens in a place like this over thousands of years is all recorded. Not just the bones of the big animals, but all sorts of plant remains, seeds, leaves, wood, and particularly pollen grains to give us a sort of readout of what kind of vegetation was here so that we can get some idea of what kind of climate was here as well.
Each soil sample adds another chapter to this story of Madagascar's past and begins to reveal something significant. Just before human arrival, the island underwent a major shift in climate.
About 1,000 years before humans arrived, we began to see the climate of this area becoming drier. Forest was opening up, becoming more of a woodland and savanna, and by the time the humans arrived, we think the animals at that point were probably in the process of adjusting to a somewhat drier climate mode.
In the story of the mega beast extinctions on Madagascar, A drought coming before the arrival of humans is significant. The trees were dry, their fruit long withered. The leaves were dead, starved of rain. Many animals, like the giant lemur, would have been driven from their natural homes down onto the ground in search of water. But such a search could be dangerous.
If the climate gets dry enough, you could find a situation where Megaladopus had to face a new challenge, and that is competition with species that it might not be thrown in with ordinarily. Having to walk farther to water, having to feed in forests that perhaps are already occupied by other species, so that the rules begin to change a little bit. Competition increases and greater risk is taken by having to spend more time on the ground.
The only water available has a jealous guardian. The lemur is cautious, but unaware of a basic law. When entering another animal's domain, keep your guard. The hunt for water was a new and stressful challenge to the giant lemur and other megabeasts of Madagascar.
It seems like that what we see here is animals trying to adapt to a change, but then humans arrive just when there's a good bit of stress already from natural climatic change, and humans then add to the challenges that these animals have to face.
Bernie had made a crucial connection. But how exactly had climate and humans conspired to destroy the giant prehistoric animals of Madagascar? Among the samples, the team discovered a further clue: a small fragment of charcoal. Bernie suspects the charcoal may point to the true cause of the megabeast extinction, not just on Madagascar, but worldwide. To test his hunch, he sets out to find more charcoal in another site. If he's right, Bernie should find not just fragments, but an entire deposit. This is Belo-sur-Mer, Madagascar. It's now a dry-caked mudflat. But 2,000 years ago, it was a massive watering hole, bounded by lush vegetation. Many animals came to drink here, but then they stopped. Bernie hopes to find in the layers beneath the surface the solution to what killed the megabeasts.
To most people, this is just a mud hole, but I call this sort of thing my poor man's time machine, because I've got a little over 2,000 years here of the history of this part of the island. It's all here in one place. Down at the bottom, we know from this kind of sediment that this was a fairly deep lake. The climate was fairly wet here, there are trees all around. Then about 2,000 years ago, the climate starts to dry out here a little bit.
As the work continues, the team begins finding bones, remains of Madagascar's rich array of megabeasts. And then comes the discovery that Bernie was hoping for: charcoal. Not just fragments, but an entire layer, 2,000 years old. This is more than the remains of an ancient cooking site. To Bernie, the charcoal is clear evidence of massive fires. Fire that could only have been started by people. As they settled the island, people slashed and burned their way through ancient forests. It was a relatively easy way of carving a foothold in the land, but one that would have drastically changed the habitat for the megabeasts of Madagascar. There must have been times when the smoke from countless fires hung over the island like a dense red shroud. Panic-stricken, the giant lemurs fled the burning forest in search of an ever-shrinking habitat. Forest destruction causes other problems. Once stripped of cover, topsoil is vulnerable to erosion. During the rainy season, tons of it get washed away, destroying yet more animal habitats. But for Bernie, it's an inevitable part of humans settling the land. And it all adds up to a package of extinction.
Try to imagine what people would have to do when they came to a new landmass. They've got to make a living there. Making living entails impacts for nature. It involves cutting down trees, plowing the soil, using the water. It implies hunting the animals, gathering food of various kinds. It involves setting fires to clear grassland and bush. It involves many things that may be quite subtle in the beginning, but quite profound later.
Big animals don't like physical stress. Add human settlement to an ongoing change in climate, and the combination could prove fatal.
Now, they survived such changes many times over in recent millennia. The difference, I think, this last time around was humans arrived on the heels of these climatic changes and brought a whole series of impacts that each acted upon the other.
If Bernie is right, no single cause lay behind the demise of the giant lemurs of Madagascar. For them, the combination of climate change and human arrival spelled doom. But could disease have played a role too?
In the absence of any evidence for such a disease, it's hard for me to take that very seriously as a primary explanation. But disease, again, like many of these others, works fairly well as part of the mix. One of the things that went wrong after people arrived.
So that was the end of the giant lemur of Madagascar. And it could be that the combination of chill, kill, and ill was the final straw for all the megabeasts. In North America, human arrival 11,000 years ago in the wake of glacial retreat, giant floods, and violent climatic change undoubtedly stressed the megabeasts. That would have made them easier to hunt and maybe more prone to disease. The giant beaver, for example, is a megabeast whose fate supports the chill theory. Yet here in Sheridan Cave, Ohio, recent evidence that the beaver was also hunted has made chill theorists think again.
I believe that people were hunting species, mega mammals, that were already endangered as a result of the profound dramatic climatic changes at the end of the last ice age.
Even kill theorists accept the idea of a link between human migration and climate stress.
I think they would have survived the climate stress if the human hunters had not been there, and opportunistically taking advantage of that stress to kill those large animals at the end of the Pleistocene.
In Australia, the oldest part of the Pleistocene world, where the extinction trail is coldest, the combination of climate and people would also fit what little is known of this still mysterious land.
Climatic change in Australia was definitely a factor, a decisive factor. On the other hand, I would also have to say it's very difficult to believe that Homo sapiens could have colonised, occupied a continent like Australia without some kind of detrimental effect.
Aboriginal nomads could have slowly settled the land, sometimes hunting, sometimes clearing and burning, maybe spreading disease, ultimately destroying the habitats of even fearsome predators like the marsupial lion. In short, what killed the megabeasts was progress. But not everyone agrees.
The available explanations of climate and human hunting and so forth have never made a lot of sense to me, just because the impact had to be so great over so many species over such a short period of time.
Ross McPhee still adheres to a single cause, the ill theory. The smoking gun, he feels, may yet turn out to be hyperdisease.
If it's the kind of disease that results in very large-scale mortality, the chances are that you're going to make the population collapse. And that's the start of going extinct.
For McPhee, this search goes on. But for all the scientists who have devoted their lives to solving the riddle of what killed the megabeasts, there's more at stake here than proving a theory.
Studying prehistoric extinctions may seem in a way like an academic pursuit that has relatively little direct application to modern life. I don't think that's the case. I think we see in the situation then something not that different from the situation we're still in today on this planet. The global environmental crisis today is really a kind of deadly mix. It's not just a series of problems lining up, waiting to be solved one by one.
In Madagascar and New Zealand, in the Americas and Australia, the search for further clues, stronger evidence, will continue to go on. Today, these lands are full of ghosts. The megabeasts are gone. Yet the combination of events that killed the megabeasts is still with us. And what or who will be next?